Recording is rolling. Today is Thursday, October 20th. Oh, all right, so we got going on. You guys know your chapter 7 problems. I'm gonna pick up tomorrow. That's these right here. We've been spending the last couple days going over these. Right? Of course, really when they go over them, I'm showing you guys like the thought process, how to solve them. So really, of course, the important idea with homework is that you have an opportunity for independent practice. Make sure you can do this from scratch by yourselves. Okay? And if you have to look at the solutions, you have to. And of course, there are always those extra problems that don't technically find, but if you want extra problems and solutions, you have those too. So I'll pick those up from you guys tomorrow. Some of you guys have already turned this in, so some of you have. I give you guys your next open notes take-home quiz. This is what it looks like right here, front and back. So I'll give you guys a few days for this. I'll pick this up from you guys on Monday. But you know what? If you knock it out tonight, turn it tomorrow, could do that, then they'll be off. Wouldn't have to worry about that over the weekend. There is at least one problem I want to take a quick look at, but we'll do that in a few minutes here. Okay, food drive. So there is a food drive going on next few weeks. I think by November, what was it? I think by November 18th, someone asked me. So you guys see a box down there by the door, and it's got the same flyer on it. All right, so I'm gonna run to the grocery store, grab some things. You guys want to bring anything in? Food drive. There you go. Donate some food. All right, so I want to talk about a few little things in this section, and then get to these FRQs. So the FRQs are going to be our main focus today, but for that. Right, so dark matter, dark energy. So my other classes, I'm showing them a TED talk, which is really cool. So I'll at least mention this. So if you guys want to look this up, Patricia for chat, and it's on dark matter and dark energy. So what I guess to try to give you guys a very quick synopsis of this. Right, so back when I was in middle school, back in the 90s, there was this question floating around of what was going to be the ultimate fate of the universe, and they kind of narrowed down to a few possibilities, but there were some conventional ideas. So suppose we're looking at the size of the universe as a function of time. Okay? Now, going back to probably, I guess there are different places I could start the story, but let's go back to, say, the 1920s. I think it was a guy named Edwin Hubble was looking up the sky and realized that all the galaxies, with a couple of exceptions, were red shifted, right? Which is evidence that they're moving away from us. You guys know if a car goes by, say you're standing on a sidewalk and a car goes by, it's like, meow. You're just hear that change. Meow. What's that called? That's called the Doppler effect, right? You guys probably know Doppler. Okay. So if someone's headed towards you, right here, a little bit higher pitch, and then it passes you, right? When it's going away, it's like a lower pitch. Well, light is also a wave, like sound is a wave. It's a different kind of wave, different category, right? But you can also be subject to the Doppler effect. So you guys know all the colors your eyes can see. Each color has a unique wavelength and a unique frequency. Right? So the more spread out is like closer to red on the color spectrum, and the more bunched together is closer to like violet. Okay, like Rory G. Biv. Right. Okay. Here, let me put like blue here, blue and then violet. Right. So, and then of course, there's more to the spectrum too. You can go infrared and radio waves and then you can go ultraviolet and X-rays and gamma rays, right? But this is like the visible part of the spectrum, right? All right, Roy G. Biv. Now, if something's headed away from us, what's going to happen is that the wavelength gets spread out, it becomes red shifted. If something's headed towards us, that's called like blue shifted, right? Because the waves get like bunched together. Well, almost all the galaxies are like red shifted. So this was some of the first hard evidence that the universe was expanding. We've known that for about 100 years now. Okay. Now, you guys know that all masses gravitationally attract. So here, I'm going to make sort of an analogy. If you take an object, say like a baseball or like this slug here, and throw it straight up, right? Well, yeah, it's got like an upward velocity, but gravity's eventually going to pull it back down. Right? Now, we know everything's expanding away from us. You can extrapolate backwards, and it looks like about 14 billion years ago, there would have been a big bang that set everything into motion. There's a lot of other evidence related to that too. This is just some of it. Okay? But there's like, hey, if everything's gravitationally attracting, moving away, but gravitationally attracting, okay? Maybe the universe is possibly going to end in a big crunch, right? So there was a big bang 14 billion years ago, everything's expanding, but everything's attracting, so there's going to be some big crunch in the future. This is just one of the hypotheses floating around, right? But you know what? If you get something going fast enough, if I throw this fast enough into the air, maybe it could reach escape speed and go away forever. So maybe everything's gravitationally attracting, but it's like slowing down, but it'll like go on. So maybe you'll have the expansion forever. Okay. And there is a sort of a third possibility, which is I could like throw this, it could go into orbit around the Earth, right? Maybe reach like orbital speed. So that'd be sort of like if it reaches like an asymptotic size. So maybe the universe like expands, but then like sort of like tapers off, right? Which could technically be possible, right? Well, about 20, 25 years ago, somewhere there, astronomers independent teams of astronomers from around the world set out to answer this question, like which of these curves are we on, right? And the answer, weirdly enough, ended up being none of the above. The actual answer, I'm sort of like spoiling this TED talk, but if you want to look into this, right, is that the universe is expanding, but it's expanding faster and faster and faster. It's actually speeding up this expansion. So this is the actual answer. Okay. So the main consensus now is that the universe is probably going to end in possibly like a big rip. It's just going to keep expanding like faster and faster and faster until it's going to end in like a cold freeze. It's right? Things get colder if you like spread out. So there's if you look at like all the matter in this room, like I've got a periodic table of the elements over there. You can say, oh, everything in this room is made out of something on that periodic table. Well, how about the universe like in general? And sort of the scientific consensus, if you make like a pie chart, right, is that only a tiny fraction, about 4 or 5% of the matter is like ordinary matter. That's something off that pie chart. Okay. You can apply Einstein general relativity and like all these observations of this like expanding universe, and most of the universe, like over half of it, is what's called like dark energy, right? So like dark energy, right? Which you need mathematically to have this like accelerating expansion, right? And then this other slice, about a quarter of the universe, is something called dark matter, which is a different idea, right? So if you look at like the rotation of galaxies, right? So take like the Newtonian physics that we've done so far. If you take Einstein's general relativity physics, which is like a more universal form, right? Turns out that Newtonian mechanics is just a simplification of Einstein's physics. Okay? Galaxies are actually like spinning faster than they should be, right? So there's actually more mass, more matter than we can really account for, and we don't know what it is. There's some hypotheses of what it could possibly be, right? But it ends up being like approximately this proportion of this pie chart. So there's extra matter in the universe, like extra mass that we can't really account for. The word dark is like dark to our knowledge what this is, right? And then there's something like dark energy that's making the universe like speed up the expansion. All right, so if you want to look more into that, that's a really cool TED talk I'm showing that to my other classes, but I just want to do a brief mention of that and move on to other stuff in this class, right? Because that's not going to be on the AP exam, right? All right, conical pendulum. Asked a couple of questions here on your take-home quiz about a conical pendulum. So at least want to throw some ideas at guys just to get you guys started on this. Okay. Could you guys take a string, put like a mass on the end of the string, like maybe hook this, right, and then wheel this around. And you guys can imagine 3D, right? Imagine it's going like going around like this could be like a cone. You guys can see that, right? Right. So at least want to get you guys set up with the free body diagram. I think you guys could figure this out, but okay. This mass has 2 forces on it. Okay. And before I draw the forces, would this be in equilibrium, like static equilibrium? No, because it's on a curved path, right? So there must be a net force on it. The fact that it's on a curved path, let me draw that curved path a little bit better, right? Means that there must be a net force on it. Okay. So this has a weight I'll call mg, okay? And there's a tension force in the string. Okay. Which force do you think is bigger? F sub t for force due to tension force. Okay. Which force do you think is bigger, the tension force or the weight? Tension? Yeah, you guys are right. Because if it was hanging at rest, just hanging out, then the tension force would be equal to the weight, it would be balanced out. Okay? But if it's like swinging around, if you feel like a centrifuge, it would definitely be more. In general, it is more. Okay? And you can probably see it just from my picture, because if you take the tension and break it into components, say, well, the tension is partially holding the weight up, and it's partially pulling it into the circle. Now you see the story starting to unfold, right? Here, I forgot to draw an angle. Suppose you have some angle here. I don't know, maybe it's like 32 degrees or I don't know, whatever angle, right? Is that angle that angle? It's the same angle, right? Okay. Do you see like a sine component and a cosine component of the tension force? Do you guys see that the cosine component of the tension is going to balance out the weight? It's equivalent in magnitude to the weight, isn't it? So tension force times cosine theta is equal to the weight. Is it? Right. So this mass here is not moving up or down. Okay. And do you guys see that the tension force times sine of the angle, which is this one here, is the centripetal force. You can say that's equal to mv squared over r. It is the centripetal force, right? I bet you guys can solve the rest of the problem from there. There's some relationship between possibly this mass, or maybe the mass cancels out, this angle, the speed that it's going. I'll do v. Although that's not a that's not a force vector. It's like a velocity vector, so it's not part of the free body diagram, right? There's some v. Right? Oh, how about this radius r? Okay. You guys think that this radius r right here, right? Which would this radius r be equal to the length, the physical length of the string times sine of this angle, right? Right. So there's trigonometry relationships for both, physical distances, but also forces, right? So we've got two things going on with that. Okay, you guys can I see that? All right, so I think that'll get you guys started on that one. I gave you guys some hints here that pretty well line up with that. But I think you guys, right? There's a couple questions there, right? All right, car on banked road. Okay. Hit this one, then we'll hit those FRQs. Okay. So let me switch my screen here because this is a problem I've been wanting to get to for a while. I really like this one. Right. You guys see some cars. Here, that sound is unnecessary. Oh, look at that motorcycle going around. Okay. Now it's a really steep banked wall. It's not vertical exactly. It's not 90 degrees, but I don't know, maybe it's like 70 degrees, something like that. Like it's real steep. Right? So there's some kind of setup here where now you might call this dynamic equilibrium. That's not true static equilibrium. Obviously, he's on a curved path, right? There's a net force on those motorcyclists, right? But sometimes you hear the phrase like dynamic equilibrium, and that might mean like maybe their radial size doesn't change, or like they're not really drifting up or down the wall. There's some speed they can go. See, like if they were going too slow, they would kind of tend to drift down the wall, wouldn't they? If they're going too fast, they kind of tend to drift up the wall. There's like some equilibrium speed they can go to like stay at that position on the wall, right? Let's get the cars going up here. Now, do you think the cars will have to go faster, slower, or the same speed as the motorcycles to like stay some spot on the wall?
Relative to the weight.
Okay, that's where the question I'm trying to get at, right? Does it have something to do with the mass? Because the cars are obviously more massive than the motorcycles, right? But you're seeing the answer right there, right? So they're all going about the same speed, which is really good empirical evidence that probably the mass and the weight ends up canceling out, whatever the answer is, right? And the question could be like, how fast do you have to go to like not drift up or down the wall? You guys can I see that? Right. Okay. You guys see that? All right. So right. Enough demo. Let's switch back over, and I want to show you guys how to solve this problem. There we go. Okay. All right. So I will show you guys two different perspectives of how to solve this. All right, one perspective is going to be like the official AP sort of perspective, which is from an inertial frame of reference. So let me do, okay, let's go inertial frame of reference. Right, which is like from the camera's point of view, that just means we're not accelerating, right? We're sitting with the camera, we're watching this thing go around. Okay, this is how AP wants you to solve all these problems. Okay? I'll do the setup and then I'll take you guys to the solution here. Okay. So we've got a really steep wall. I'll draw my wall really steep, just like the demo, so that it matches, right? Got some crazy angle from the horizontal. I'll call it theta. Okay. We got this car. Okay. Yeah, we're looking at like here's the taillights of the car. Here's the license plate. We're watching it like go right behind this car. We're watching it go around, right? Can you guys see it like going into the page and like curving around, kind of like this, like kind of in a turning. Okay, but with some speed, I could call that speed like V, right? Like in the page, like V. Okay. I want to be careful how I draw this. I don't want to get my diagram too cluttered because what's really important are the force vectors. So I'm going to break out the pink ink and do some free body diagram force vectors. And there are only two forces on this car. Okay, and I bet you guys could figure them out. Okay, isn't there a weight that's pulling the car straight down? Okay, so I will label that mg for weight. Yeah, label that right there. Okay. And what other force acts on the car?
Normal force.
The normal force. Right. Now, if you had a flat road, you guys know the normal force is equal in magnitude to the weight. Right? Wait, did we do something like? I don't think I ever did like the fact that the Earth spins. Right. Here, let me mention it just real briefly. Right? The fact that the Earth rotates, the normal force is technically like 0.5% less than the weight, because the Earth is like spinning. If the Earth was spinning too fast, you like fly off the face, right? So there's a tiny subtle effect. But we usually ignore that. Right? We say the normal force is weight, but that's not going to be true on the space road, right? Now, imagine this car like wheeling around, zoom, zoom. Right? Do you think that the force that the road feels, like suppose there was like a giant like linear bathroom scale and it's just like going like, so you could read the force, right, which would be the normal force. Is that going to be more than or less than the weight of the car? Zipping around there. More than, for the really similar reason that the tension and the string, the conical pendulum was more than the weight of the bob. Okay. So normal means perpendicular, right? So I have to hold my, see, I'm holding my ruler perpendicular to the surface. Here's the surface. Here's my ruler. See how there's a 90-degree angle there? There's that. Okay. I'm going to draw the normal force greater than the weight. Do you guys see F sub n, like the normal force? You guys see that? Okay. And if you break that normal force into components, I'm going to go ahead and do components that are aligned with Earth's gravity for this inertial frame of reference. Okay. You guys see that the normal force is partially holding the car up and partially pulling the car into a circle, like pushing the car into a circle, right? Okay. Do you guys think that this angle theta looks like this angle theta? Right? Like if that's 70 degrees, that might be 70 degrees. You guys see that? Okay. Same thing. Okay. So here is this component is normal force times sine of that angle, same angle, okay, which is the centripetal force. So I could call it mv squared over r, where r refers to the radius of curvature. Like, could you guys imagine, probably pretty close to the edge of my paper right here. Okay, might be like the axis of rotation that this car is like sort of going around, right? Okay. And there, this distance could be r. Let me sort of try to draw that, but not clutter up my picture that's already there. Okay. So from this axis of rotation to where the car is, I call this like radial distance r as it's going around. You guys see that? Like r? That's what that r is. Okay. Okay. And okay, so this is equal to this. Okay. Oh, how about the normal force times cosine of theta? Isn't that equal in magnitude to this weight equals mg? Same thing? Isn't that true? Okay. So then what you can do is you can set up an expression. How about okay, so normal force times sine theta is equal to mv squared over r. Normal force times sine theta equals mv squared over r from your lab. Right, that's the. Right. If this was an AP multiple choice question, the multiple choice answer to what force is the centripetal force would be the horizontal component of the normal force. That's what that is, right? The horizontal component of the normal force is the centripetal force. Okay? Or is applying. Okay? And then we've got the other expression, normal force times cosine theta is equal to the weight of the car, right? Because that's holding that up. Sure. So we have, you guys see a system of equations right here? System of equations. There's a system. Okay. And turns out if you divide one equation by the other, which is a valid algebra step, you guys see that the normal force is going to cancel out. Okay. The mass of the car cancels, which we said it was probably going to happen. Okay. Guys, what is sine divided by cosine? Tangent. So tangent of the angle is equal to v squared divided by r divided by g. I call it like v squared divided by well, r times g or g times r, however you want to do that. Okay. Now we have an expression that relates a bunch of properties of the setup. Right. So I see an angle, I see a speed, I see a gravity field, I see this radius that's going around. If you know any three of those four, you could solve for the other one. Right. You guys kind of get that? Okay. And then if you want to like solve for relationships, blah blah blah. So if you knew the angle, if you knew the gravity field, you knew the radius, which was all set up in that problem solve, you could solve for the speed of the car that has to go to like not drift up or down. You guys can get that? Okay. All right. Let me solve this a different way with you guys. Different way. Okay. You guys get that? All right. Now, the way I'm gonna solve this. Okay. If you guys ever turned off your brain in this class and like didn't learn anything, just like tuned out, these next 5 minutes would be it. All right, because I'm going to show you guys how you can solve this from a, what did I say? So before I call this inertial frame of reference. Okay, let's switch the point of view. So point of view, okay, let's go what I could call dynamic equilibrium. Okay, now what I'm about to do, never do this for AP, FRQs, multiple choice questions. Never do what I'm about to do because AP doesn't like this. But I want to show you guys how you can get the same answer from a different point of view. Right? what if you're along for the ride with the car and your interest is more like, I just don't want to drift kind of up or down this incline. So let's redraw this incline. Okay. Right, got ourselves a car, right, center mass, wheels, tail lights, license plate, whole deal. Okay. Right. And you guys remember for inclines, what I've usually done is introduce a coordinate system that runs parallel perpendicular to the surface. Right, so I'll go ahead and do it on this one. I didn't do that on the last one. Well, not really. Okay. I did everything aligned to graph, but well, for this one here. So draw my angle data. Okay. Same setup as before. Okay. But now let's do from the point of view of if you are inside the car along for the ride, and the faster this car is going around, doesn't it feel like there's a centrifugal force pushing you out? Right. That's from the point of view of dynamic equilibrium, right? So, okay, now here's where there's like a fictitious centrifugal force, or maybe you could say the equal and opposite force, the actual centrifugal force. So this could be like the force acting back on the road, right? So I'm going to draw like this. Okay. Now I've never drawn any kind of centrifugal force, have I? But that's kind of what this would be, right? Or you could say it's the equal and opposite force to the true centrifugal force on the car. But this is the force back on. It's sort of like this. Now it's still equivalent in magnitude to mv squared over r, right? Still that. Okay. Now this car, of course, has a weight pulling it down. So trying to things to scale, right? Okay, I think this is going to work pretty close. Okay, and I can still call that weight mg. Okay, and there's a normal force from the road that's like the way I'm going to draw this is as if it's all balanced. If there's zero net force, so I'll call this the normal force. Okay, I mean, if you didn't have any other context, does it look like those three vectors cancel each other out and there's zero net force, right? Okay, that's not really what's going on, but from the point of view of like being inside the car, you might feel like relative to like some place in the road, like you're not really drifting up and you're not really drifting down. Okay, right? This is a weird way to do it. Okay? And I'm going to take say what's aligned to this rotated coordinate system. Well, the normal force already is, so I'm okay with that. But these two, I'm going to break into two components. Okay, so the weight is partially trying to make the car pull down, right? But it's also partially pushing into the road. Right? So I've got these two components. Okay? And this fictitious centrifugal force, right, which is a term I almost never use in this class, right? Don't ever write the word centrifugal on an AP exam, right? It's partly trying to make the car sort of drift up the road, right? And also partially pushing into the road, right? I said, whoops, I meant to dash that a little bit better. That's supposed to be dashed, right? It's a re-representation of this. Okay, now this angle theta, how does that translate? Well, I think that angle theta also pops up here and also pops up here, right? A little tricky to think about, but I think you guys can figure that out, right? Okay, so here's the key. If I don't want this car to be going too fast and drift up or going too slow and drift down, don't I want these two components to balance each other out? Okay, and here's your mv squared over r cosine theta. And here's your mg sine theta, right? Is that okay? And I would want those to be balanced out. So say they have to be the same magnitude. So the mg sine theta must equal the mv squared over r cosine theta, right? Is that okay setup? Okay. Now the math still cancels out, so that's all fine and good. Oh, I could take the cosine, divide it down here, take the g, divide it by here. So sine divided by this cosine, that gives me tangent on the left side. And then I got a v squared over here, divided by, and I could divide this g down and get g times r. Hey, is that the same expression we got before? Right? Using a totally different point of view. Right? It's the same thing. You see it? Right. So there's two totally different paths through the forest to get to the correct, same expression, same answers. You see it? Right. I want to take this one more wacky step, which is this normal force. So let me go back to this inertial frame of reference. The normal force. Wouldn't the normal force just be, well, I see normal force times cosine theta is the weight. So wouldn't it be true that the normal force is equal to the weight divided by cosine theta? You just take this expression and rearrange it and say the normal force is the weight of the car divided by cosine of the angle. Okay, so that's the normal force, like the true total normal force from the road, right? Okay, now over here, well, I've got this. Looks like this is balancing out with these two components. Wouldn't that be true? Okay, and this component is your MV squared on R sine theta. And this is your weight times cosine theta. Okay, so from this point of view, the normal force is pretty much the sum of these two, but this and this and this have to balance out. So the normal force is mv squared on r sine theta plus mg cosine theta. Right, is it? Now, at a glance, that crazy expression looks nothing like that, right? In fact, they even have different variables. This doesn't say anything about the v, although this does, although I guess you could substitute this and you could do some crazy math, and I bet they have to be the same, right? Okay. So I was working on this last night and so, okay, that's pretty crazy. So I just made up some random numbers. I made up a random mass of the car, random radius of curvature, random blah, 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 blah. Right? And it turned out they gave me the same answer. It's like, okay, so I guess that actually did work. Okay, so there you go. All right, so totally killed that one. There you go. Want to at least cover that. It's bit of fun. All right, you guys ready for FRQ? FRQ. Oh yeah.